Okay, while set up, let me introduce our second speaker. So, second speaker is Andrea Botteon. He obtained his PhD in astrophysics at the University of Bologna and INAF-IRA Institute of Radio Astronomy in 2018, with a thesis on shock waves and nocturnal phenomena in emerging galaxy clusters. From 2019 to 2022, he worked as a postdoc researcher at the Leiden Observatory in the Netherlands, where he specialized in low-FAR radio reduction, becoming also an active member of the team carrying out the low-FAR 2-meter sky survey. In 2022, he was awarded a Young Researcher Grant, congratulations for that, from the Italian Ministry of University and Research, and started a fixed-term position at INAF, where he became permanent staff researcher in March 2023. So his main interest is study of nocturnal phenomena in galaxy clusters, combining observations from radio telescopes and X-ray observatories. And today is going to talk us about the prototypical galaxy cluster merger. Floor is yours.
Thank you so much. Can you hear me well? Yes. So thank you for the introduction and thank you for being here. So as this is the high energy seminar, I thought to talk about something very energetic, such as galaxy cluster merger. Sure. Okay. Oh. Okay, so let's start with a bit of context. So this is an image from a numerical simulation of a large-scale structure in the universe. We can see that the matter is not distributed uniformly. We have very long filaments of matter. We have underdense regions, which are the cosmic voids, such as this one. And we have overdense regions, the knots of the cosmic web. So these knots are the galaxy clusters, which are the most massive gravitationally bound systems in the universe. And they are composed of hundreds to thousands of galaxies that are bound together by gravity. Here you can see an optical image of a galaxy cluster. Despite the large number, galaxies only constitute a few percent of the total cluster mass, which is dominated by 80% by dark matter that we cannot directly observe. The majority of the baryons in cluster are not in galaxies, but are in the form of intracluster medium, or ICM, which is a hot and rarefied plasma which permeates the entire cluster volume, and that it emits in X-rays via thermal Bremsstrahlung. Some galaxy cluster also shows presence of diffuse synchrotron sources in the ICM that underline the presence of cosmic ray electrons that are diffusing in magnetic fields that are spread over the entire cluster volume. And these sources can take the name of radio halos or relics, depending on their properties. Just to give you a more detail on this kind of sources, radio halos that are located in the cluster center, they have a morphology that recalls that of an X-ray gas. They are unpolarized and they typically show steep spectra. This is the typical values. This is and I'm using this notation for the spectral index of the synchrotron radiation. Radio relics instead are located in the outskirts of galaxy clusters. They also cover megaparsec scale. They are elongated and arc-shaped. They show high degree of polarization. These are the electric field vectors, for example, of this relic. And they also have steep spectrum radio source, although the spectrum of relics is a bit flatter compared to that of halos. And they can be found in a single or even double systems, double relics. So the formation of these kind of sources is strongly related to the formation process of galaxy clusters. So clusters form hierarchically through cosmic time as a consequence of aggregation of matter through galaxy cluster mergers that are very energetic events. They inject up to 10 to the 64 erg in the ICM, and this energy is dissipated by shocks and turbulence, mainly into the heating of a gas, which led the ICM to reach temperature of the order of 10^100 of Kelvin. And given the low density and the magnetic field in the ICM that are of the order of microgauss, we have the ICM is a high beta plasma. So during this formation process of cluster, radiohalos and relics are formed in the ICM. So this is something that is unavoidable in the process of larger structure formation. So what are the current favored model to explain these kind of sources? So radiohalos, we believe that they are powered by turbulent reacceleration of particle, where the turbulence is injected by these energetic events. And through a complex chain of mechanisms, the energy is converted from the megaparsec scale of cluster down to the particles scale, where the energy is transferred to electrons. And by diffusing in the magnetic field, they generate the synchrotron radiation that we observe. So this is an efficient process, is a Fermi-2 mechanism, and this means that the particles that are accelerated are already relativistic in order to generate the observed synchrotron luminosity. And that's why we talk about turbulent reacceleration of seed particles. Radiohelix instead are associated with shock fronts located in the cluster outskirts and that are propagated in the periphery. And we know that shocks in astrophysics can accelerate particles via diffusive shock acceleration, DSA, which is a Fermi first mechanism in which we can relate the slope of the accelerated particle with the Mach number of the shock that has generated the population of relativistic electrons via this formula. So one problem in explaining radiohelix is that the shocks are associated with these kind of sources are very weak and very inefficient to accelerate particles if these are accelerating from the thermal pool. And that's why now the reacceleration also for the shock, and this requires the presence of a population of pre-existing relativistic electrons at the location of the shock fronts in the ICM. So today I will talk about this cluster Able 754. This is a massive and low redshift cluster. Here you can see its main properties. It is known to host both a radiohalo and also a relic. This was claimed in the past. And is also famous to be one of the first cases where a shock front has been clearly identified with Chandra. So this is the Chandra temperature map of the cluster. The contours are the X-ray emission. We can see that the cluster is quite hot. The temperatures are even above 12 keV. And in this elongated structure, the temperature is lower. This region is the remnant pool core. So is what is left after the merger of a core that of one of the two clusters that generated the condition. This instead is so in the background, we see the X-ray emission, but we can see that is elongated in the east-west direction. This is the remnant pool core that I was mentioning before. And the contours in this case denote the weak lengths analysis, where you can see that also from the optical analysis, we have an indication that the matter is distribution preferentially along this direction. Finally, here I'm showing the X-ray radio overlay. So the image in the background is the Chandra image. This arc is the shock front identified with the Chandra, and the contours are the GMRT images are coming from GMRT images that show the presence of a halo located in the cluster center and the presence of this source that was called relic, because it's associated with the shock front on the left. As this is a low redshift cluster, in order to study it and to increase the signal to noise of the diffuse emission, these images have to be done at low resolution, and that's why the relic appears blended with the halo. So this paper by Macario was the last one that investigated the radio and X-ray property of the system. It is a very nice system, but it has been quite overlooked in the past. And recently, last year, we published a paper using a new observation coming from MIRCAT and XMM. Here you can see the name of my collaborators. So what kind of data did we use? We used the MIRCAT 10 hours observation with the ultra high frequency, so at frequency of 820 megahertz, and 10 hours observation in L-band, so 1.3 gigahertz. For the X-ray, we used a deep observation with XMM consisting of 13 observation AD. I will start showing you the XMM image. This is an image that covers a much larger scale compared to the Chandra one. This is 1 megaparsec. And we can see quite clearly the bow shock identified by Chandra. And by the way, this is the field of view showed before. So they are covering much larger scale. And this is the MIRCAT ultra frequency image. Let me show it at slightly lower resolution to increase the signal to noise of the diffuse emission. Again, we can see that. So first of all, we don't see a clear arc-shaped emission at the location of the shock front, or we don't see a relic. We see a volume filling emission that is bounded by the shock front. And this is indeed a case of halo shock connection. We don't find a relic. Okay, in order to produce this very, very nice MIRCAT image, we have developed, we have actually used, some pipelines that were originally developed in the Lofer collaboration to calibrate the data. I won't go into the detail, but I really want to mention this because this is discussed quite extensively in our paper, because indeed we used a new method to calibrate the MIRCAT data, adapting and the pipeline used by the Lofer team on MIRCAT, and compared to what we published in 2021 in this paper, where we used direction independent calibration. In the past year, the script has been improved to deal with the direction dependent effects. So basically, we are now able to calibrate for ionospheric errors that are present, for example, in these sources across different regions of the field. And this is particularly relevant if we want to achieve the best quality possible in our radio images. And this was applied to MIRCAT for the first time. Going back to the science, the real science. So this is the halo. Here you can see the image at 820 megahertz, and here it's at 1.3 gigahertz. You can see that the halo is more roundish at 820 megahertz, while it's more elongated in the east-west direction at 1.8 gigahertz. Its largest linear size is 1.6 megaparsec, and the spectral index is 1.3, and the power is this value, which are typically values for radio halos. This image shows the nice multi-band overlay, optical X-ray, where X-ray are blue, and the radio, where radio is red. You can see that the radio halo sits quite nicely on the thermal gas emission. Indeed, these images cover this field of view. By combining the data of ultra frequency and L-band, we can study not only the integrated spectral property of a halo, but also the resolved spectral property of a halo, and producing, for example, a spectral index map, which is shown here. So the color bar shows the spectral index values. We can see that at the center of a cluster, we have a median value of 1.3. While we have different spectral index in the east-west direction. Here is more red, so flatter spectral index, and also here. While in the northwest direction, the spectral index are steeper. So we have that the merger is along the east-west direction, and the spectral indexes are flatter. And across the orthogonal merger axis, we have steeper spectral index. And this might indicate that there is a different efficiency of particle acceleration at different position in the cluster. So we'll go back to this point. So additionally, there is we discovered this elongated structure in the periphery of the cluster, which is not very clear in this image. It's very faint. It is at almost 2 times R500, and we classified it as a radio relic because it's peripheral location and very long extension. So here you can see the images at 820 and 1.3 gigahertz. Here are the properties. So again, is an emission that covers 1.6 megaparsec in largest linear size. What is interesting about this source is its radio power is quite weak, and this is interesting because, as I was mentioning at the beginning, particle acceleration at the cluster shock is very problematic because of the weak Mach number of shock fronts in the ICM, and this is problematic because radio relics generally have high luminosities. And this is not possible to reconcile with the DSA theory of acceleration of thermal electrons, given the high power. So finding a radio relic with a very low luminosity is quite interesting, especially also because this radio relic is quite large, meaning that the power is low, but the dissipated energy through the shock surface is quite large because this depends by the shock surface. In this case, we have a surface which is probably of 1.6 megaparsec. So this means that we are probably a lot of energy that can go into particle acceleration. So we wonder whether DSA was viable in this system. And we produced the so-called efficiency plot, which is shown here. So basically here, eta is the efficiency of electron acceleration. So how much, or what is the fraction of the kinetic energy dissipated by the shock surface in order to reproduce the relic luminosity as a function of the magnetic field downstream. We don't know the magnetic field, so that's why we computed the efficiency as a function of B. So let's focus on the blue line for a second. We don't even have the detection of a shock, but we can use the DSA relation to start from the spectral index of the relic to derive the Mach number implied by DSA and compute these quantities. And it turned out that for values that are viable for DSA of thermal pool, so below 10 to the minus 3, and for magnetic fields that are feasible in the outskirts of galaxy cluster, this relic seems that could be generated directly by DSA. So this is we know about 30 radio relics in the literature. This is one of 2, 3 where DSA is not ruled out. Okay, with XMM, we studied the thermal gas properties of the ICM. We produced the temperature, entropy, and pressure maps that you can see here. Here, I reported some interesting feature. So we have the cold remnant core that I mentioned at the beginning. The shock front is located here. Here, the jump in temperature is not very clear because the temperature map is cut precisely at its location. We found another region of shock-heated gas, we call the second putative shock region here. And we also noticed the presence of this extension in the tongue, which is characterized by low values of temperature, entropy, and pressure. And this might be also mirrored in the north, in this region here. We call northern putative tongue emission north. So if we look at the radio halo now, and we have a complete picture of what is the morphology of radio emission, the morphology of X-ray, and the spectral properties of radio emission, and the temperature of the gas, we have indication that in this region on the west, where the radio emission seems to jump, the surface brightness of the radio emission seems to jump. We also have a surface brightness jump in the X-ray, and we have indication of a shock-heated of a hot gas. So this suggests that we have basically a counter shock in the opposite region compared to the previously claimed shock on the west. Okay, so this cluster was known to be a known head-on merger since the past. This is the results of a simulation by Röttger in 1998 that tried to replicate the merger, so the morphology of X-ray emission. These are the parameters of merger. And here you can see the temperature. So already from this simulation, we were expecting a shock front in this region of the ICM. So we wanted to interpret the new feature observed in X-ray and radio in the context of this merger scenario. So basically, we start with two clusters that probably don't have an equal mass that are merging with a non-zero impact parameter. As they approach, the gas between them is compressed by the collision and is squeezed, and it moves in perpendicular direction compared to the cluster merger. And in the stage where we are observing the system now, these tongues are developed, and we have the shocks on the left and on the right side of the system. So this is a sketch. We found that also in numerical simulation, in the idealized simulation, we can find similar features. These are a simulation by John. And you can see that in the simulation, you can precisely see the developing of these outflows of materials along the perpendicular direction that are characterized by low temperature, as was observed in Nebel 754. And we proposed that this outflowing material is driving the shock front that is generating the radio relic in the equatorial direction compared to the main cluster merger axis. So this is my last slide. So another thing that we wanted to do is study the possible correlation or anti-correlation between the spectral index of the synchrotron radiation and the thermal properties of a gas. Why this? Because this might contain information about the acceleration efficiency of a process and the level of gas heating or mixing, so turbulence in the ICM. This is something that I did myself in 2020 for another system. This was, in that case, we used a few resolved regions in the cluster, and this has been done also by others after that. For this case in particular, we wanted to correlate the information on a pixel-to-pixel basis. So we have very nice spectral index and temperature map and pressure and entropy maps. These were correlated on a pixel-by-pixel basis, and these are the results. So this is the spectral index versus temperature, entropy, and pressure. We don't see any striking correlation or anti-correlation. Perhaps we see an anti-correlation, especially if we focus in this central region where there is the bulk of a pixel in our maps. We might see an anti-correlation between spectral index and pressure. And this is what one can naively expect, because the region where the spectral index is steep are a region where probably there is less turbulence, so the efficiency is lower, and the pressure is also lower. And the region where the spectral index is flatter are a region characterized by high level of turbulence. However, the scenario is much more complex than what I've described, because these thermodynamic properties are not good proxies of the turbulence in the ICM, and that's why we have GRISP now that is doing a lot of measurements of the turbulence in the ICM. The scenario is also made complex by the fact that the heating and cooling time of a thermal gas is different compared to the particle acceleration and cooling of the relativistic electrons. And also there are other factors such as the degree of plasma collisionality that affects the efficiency of particle acceleration. So this kind of correlation needs to be studied more in detail to understand if they are telling us something. So jumping to the conclusion, Abel 754 is really a prototypical major cluster merger. Thanks to the new Meerkat data, we have provided an entirely new picture of this spectacular system. In particular, we have revised the nature of the diffuse emission associated with the east shock. This is not a radio relic as claimed in the past, but it is a part of a halo that is bounded by the bow shock. We also discovered a faint and distant radio relic in the outskirts of the system, which is in principle compatible with DSA. We also studied the thermal gas property with XMM and found evidence for a shock-heated region, so a shock front in the opposite region of the eastern shock, and low entropy and pressure and temperature tanks. And we also interpreted the entire observation in the context of a non-head-on merger scenario. The results of this talk are presented in this paper. You can see that this is paper one. Indeed, there are other papers in preparation concerning the analysis of these very nice data sets. So stay tuned for more, and thank you for your attention.
There were questions from me?
Thank you for the nice talk, Andrea. I have two questions. So first, if you see spectral index map of the halo at to the eastern shock, so spectral index is flat, correct? Which is expected for radio relics.
Here.
To the
Yes,
east,
yeah.
okay? And since there is also a shock fund, so can you clearly rule out that the emission is not related to shock and it's only halo emission? Because, or is there any information from polarization side? Because relic can be faint, okay? And there are, as you talk, that there are some systems where you see shock, like halo, with an edge, which is a shock fund. So can it be also a connection between, physical connection between, let's say, first particle are accelerated by turbulence, then they again re-accelerated by shock passing through that? Is there any way to rule out that?
Thank you for a question. Of course, we have Meerkat data with the polarization. So a way is to study the polarization of the shock and check whether we have high degrees of polarization, such as in relics. For the other cases where we have the halo bounded by the shock, there are no indication of polarized emission. But
Plus also in those cases, there is no evidence of flat spectral index. As far as I remember, okay, although we need high quality data like that, but for example, in case of toothbrush, because it's very faint, so but spectral index is also not flat like in this case. So since it's very bright here, and you can also study at very high resolution because of the low redshift, so it
yeah, indeed.
check that.
One point is on the polarization, indeed, and that's one of the paper that is in preparation. The other point is a real detailed analysis of the shock front region. So in that case, we want to combine the XMM and the Meerkat data, ultra frequency and L-band to study really the profile of the spectral index and the surface brightness profile of a radio emission across the shock to see if we have indication of really flattening of emission close to the shock front detected in X-rays. So yeah.
So it's about this farther relic. So so first, how can we explain the presence of a shock fund considering the merger scenario that you propose, correct? This one, and also how this particular relic falls if you see all these largest linear this size and distance, all those relations with mass and spectral index.
So I have
because it is so far from, I'm like so distant from the cluster center, and considering the merger scenario that you discussed, how a shock fund can be there to the southwest.
So neglecting the simulation of John that is analyzed, you can see similar shock front in a similar location in basically all simulation. These are a simulation by Zhang. Again, this is a binary merger, and in this location, which is basically orthogonal to the main merger axis, you have the development of a shock that is moving also with some angle that might be similar to the case of Eber-754. So it's not even perfectly equatorial compared to the merger axis. And these are other simulation by Wonky, where you have equatorial shocks at very large distance from the cluster center, and this is what you would expect if these shocks are those that are generated during the early phase of the merger. So when the plasma is compressed. In this phase, the outflows drive this equatorial shock, and at a later stage you have the axial shocks. So it's good that we see these in simulations.
Any more questions?
So, following up on this, on the X-ray side, the 7-ton looks like it has a scale which is comparable to the scale of the whole cluster.
Yeah, it's I would say more than 1 megaparsec long.
So how fast does that gas have to be moving to be ejected that far out in the time scale of the collision? How far would you expect it to go if it's moving that fast?
I don't have an answer on this. We should definitely look at simulation. Maybe John, you have an idea?
It's a cold lens. It's cold now.
It's
According to temperature maps.
It's cold, but it's fast moving, right?
Remind me how fast again?
Sorry.
Remind me how fast again?
Oh, the question is how fast can it be? How fast can be these outflows in perpendicular directions?
Yeah, we can check that pretty quick. Can do that this afternoon. I don't know off the top of my head, so.
Any more questions? I might have a couple. Can you go back to the plot of the efficiency function of the downstream magnetic field? I was just curious, do you need to assume in the plot that there is an amplification at the shock beside the normal compression, or what do you assume for the magnetic field? You don't have the measurement of the magnetic field upstream, right?
So I have actually the precise equation that we are using, which is this one. So this is the radioluminosity. I actually have the labels here. Okay, so this is the relic radioluminosity, and this is what we observe in radio. So that's a number. This is the dissipated kinetic power through the shock surface. This is the shock surface, the density of a medium, and the velocity of a shock. We don't have the velocity of a shock because we don't have a shock, but we use the DSA using the temperature and the pressure obtained from the universal profiles by the X-scope team. So we use the values that you would expect at that region of the cluster, and from that we derive the velocity of the shock front. Eta is our free parameter. This psi is a fraction of, it takes into account how many of the accelerated particles are actually visible in radio. And this is the factor that takes into account the radiative losses. So BCMB is the factor that takes into account the inverse quantum losses, and B is the other free parameters, that is the magnetic field downstream. Concerning the need of amplification of the shock, post-shock, the details are not really relevant for this calculation because, again, we don't have a value of B. We just assume different values and compute the efficiency as a function of different downstream magnetic field strengths.
Okay. And maybe one question.
No, we have to move on.
Right.
It is not.
Okay, right. Well, let's thank Andrea, both speakers again. Then don't forget this week we have also a special seminar on Monday, usual time here.